Look up on a clear night, and your senses tell you a very convincing story. The ground beneath your feet feels perfectly still, while the stars, the moon, and the sun sweep in massive, predictable arcs across the sky. For thousands of years, humans used this exact observation to survive. By assuming we sat at the dead center of a rotating universe, our ancestors could track the movements above to predict the changing seasons and know exactly when to plant their crops. They built massive physical calendars to measure these cycles. Structures like Stonehenge were precise architectural tools designed to align with the sun's path and physically map the solstices. Placing Earth at the center of everything was a highly rational conclusion. It perfectly fit the data our eyes and bodies were giving us. This illustration shows the formal mathematical version of that idea, known as the Ptolemaic or geocentric model. Formulated by the ancient Greeks, it mapped out a rigid system of spheres carrying the planets and sun around the Earth. But as generations of astronomers kept measuring, a problem emerged. Certain planets didn't move in perfect arcs. Occasionally, they would slow down, loop around, and appear to travel backward against the background stars. To force their Earth-centered math to match these new observations, astronomers invented epicycles. They proposed that planets were orbiting in tiny circles that were themselves orbiting in larger circles. By calculating these overlapping loops, they could actually predict where a planet would appear. But the geometry required to make it work grew increasingly tangled and messy. A scientific model can only support so many corrections before the underlying structure simply breaks down under the weight of the raw data. This diagram illustrates the radical solution proposed by Nicolaus Copernicus. By removing Earth from the center and replacing it with the sun, the bizarre planetary loops disappeared. The math became elegant again. But this heliocentric model faced fierce opposition. It defied the authority of the Church and centuries of accepted philosophy, and Copernicus didn't have the definitive physical proof needed to show the Earth was actually moving. That proof required precision measurement. Enter Tycho Brahe, an astronomer who spent decades meticulously cataloging the exact positions of the stars and planets using massive naked-eye instruments. After Brahe died, his assistant, Johannes Kepler, inherited this mountain of data. Kepler applied strict mathematical logic to the numbers, trying to map the true shape of the solar system. A clever idea means very little in science unless you have the objective measurements to back it up. Kepler finally had those measurements. The data revealed a surprising truth. Planets don't orbit in perfect circles. Their paths stretch into an ellipse, with the sun sitting slightly off-center at one of the focal points. Kepler defined these movements through specific laws of planetary motion, providing mathematical proof that the planets follow predictable physical paths around the sun. While Kepler crunched the numbers, Galileo Galilei looked through two small pieces of curved glass in a newly invented device called the telescope. He observed that Venus went through phases, shrinking to a crescent and growing full, just like our moon. If Venus orbited the Earth, this geometry would be physically impossible. It had to be circling the sun. These notes from his book Sidereus Nuncius show sketches of 4 tiny stars orbiting the planet Jupiter. He had found clear empirical proof of a celestial body that did not revolve around Earth. With new optics extending human sight, the raw physical evidence dismantled the ancient illusion of a stationary Earth. The Copernican model was mathematically sound, but a glaring question remained. If the planets were flying through space in massive ellipses, what invisible force was holding them in their orbits? The answer arrived with Isaac Newton and the publication of his Principia Mathematica. Newton identified the universal law of gravity. He realized that the exact same force pulling a falling object to the ground on Earth is what keeps the planets tethered to the sun. The cosmos was no longer a realm of divine mystery operating on magical rules. It was a mechanical system driven by consistent, observable physics. Understanding this required an enormous leap in human perspective. We had to accept that our home is not the anchor of creation. Instead, we are all just passengers on a massive rock, hurtling through a vast, dark expanse at incredible speeds. Mapping the solar system forced us to rely on instruments and mathematics rather than just trusting our raw senses. By rigorously testing hypotheses against hard evidence, we built a method to separate comforting illusions from physical reality, and that commitment to objective truth is exactly what allows us to explore the stars today.